Hello, welcome. Welcome to my keynote presentations about the study of equivalent level of safety of small unmanned aerial vehicles. This is a keynote for the GSEAME 2021, the Global Summit on an Expo on Aerospace and Mechanical Engineering. I'm very pleased to be invited to make that presentation to you, to the you colleagues, and I'm Luc Rolland, lecturer in robotics, automations and controls at the University of the West of Scotland, located in Paisley near Glasgow in Scotland in the United Kingdom. First of all, we know that small UAVs have been in use quite a lot around us. So I'll have a look at them and their capacity to be safe. And first of all, the first topic we need to examine together is their equivalent level of safety. We'll go through a bit of history. The introduction is started. We're going to go through definitions, regulations, and challenges, continue with the problem statement, and then we will be assessing the current level of safety. And this leads to more details in terms of estimating ground impact risks, estimating mid-air collision probability, and the way to be enhancing control and situational awareness. And we will conclude this topic. History of radio planes. Well, the RC vehicle started with Nikola Tesla first. Officially, he had patents and he had made them work. I think he made two. One of them, which was a submarine, and I think another one, which was actually a flying drone. Uh, Now, the most important one is this figure here that we see on the right there, which happens to be Marilyn Monroe assembling drone aircraft for the military, the US military, at the end of the 40s and at the beginning of the 50s, before she was discovered to become a Hollywood actress. So she was called originally Norma Jean. Uh, the militaries were the first to use drones, small drones, because they were good for the 3Ds that the militaries had identified, which we do identify in the civil operations as well. Dull, dirty, and dangerous. Dull because we need something that is persistent. This means over hours and hours, it has to do the same quality, the same job. Persistent aerial surveillance. Dirty, well, especially when you're dealing with forest fires, things which, well, are not very convenient for humans and are not very making them very comfortable. So dirty is one of those. And of course, dangerous, meaning that, again, nuclear fallout could fall into this one as well. Target zones, target places, danger zones, areas which are under conflicts, under pressures, under the effects of the environment, which means a risk to humans. Well, the expansion to civilian roles was for weather monitoring, hurricanes with the Aerospace is an example. Coastal border surveillance, the first country to really achieve success with that was Switzerland, to guarantee its border controls with fully autonomous vehicles around their border, checking against Austria, France, and Italy, and Germany. And then environmental monitoring, and this is what we did with the project Raven 2 in Canada, checking what the environment could produce and then be able to act upon this after that, relay information. Police search and rescue duties, traffic monitoring over densely populated areas with streets, highways, and of course, train lines. Media usage for any kind of activity that the media may see fit, where they want to be watching from a distance. Cinema in action movies have been in use. Aerial photography, like for sports, wildlife, real estate evaluations and valuation. And then aerial delivery, which has been made very popular with Amazon and the like. Typical small UAVs here you will find are classified in Canada and USA. It's below 25 kilograms overall. Okay, that's those examples that are relatively small. Okay, although sometimes they're big enough that they may not fit into the trunk of your car, but they may fit on the trailer with the wings folded. So ideal for low altitude, long endurance missions, what we call LAL missions, and they last usually for 8 hours. That's why we mostly use fixed wings. Quad rotors, for example, rotors, octo rotors do not last more than 30 minutes, perhaps 45 minutes at the most. So they're not very efficient for LAL missions, and which is what the world wants. So we have UAVs, so we have those robots which are flying, and these are robots. So they are an aircraft which contain a certain amount of control with sensors, which allow them to be programmed and to do a certain missions. Another name is often we use UAS, unmanned aerial systems, or instead of vehicles. And then another translation is drone. That's the popular word for UAVs. And then this means we have to define that they could be automation and they could be autonomous. Automation means you put the program there measuring from sensors, having a task to perform. It does the task and it comes back to its original point. That's automation. That's predefined in predefined conditions. That's what we do mostly in robotics with sensors often inside the robot themselves. And that's it. That's automation. But then if you have varying conditions, things which may arise, perturbations, uh, unaware situations which may impact the missions, which the program doesn't know, but the system should adapt to it. This is what we call autonomous operations. The system has to finish the mission and has to cope with the problems which arise. Okay, and that's where autonomy starts to work. The regulations with UAV started in 1944 at the Chicago Convention, where we call that no pilot on board. Here's the quote. No aircraft capable of being flown without a pilot shall be flown without a pilot over the territory of a contracting state without special authorizations by that state and in accordance with the terms of such authorization. Which means that if you're not piloted, you need a special authority to grant you the right to do this. What are the challenges with UAVs? Here's an example of the giant big stick. It looks, well, it does quite a lot of jobs there. It's a small vehicle, so I can transport that by hand. I can fly it by hand. And actually, this is having a very simple system of controls there. And this may be considered inadequate for anti-collision technology. So we have to worry about the controls there. We have to worry about the sensors and all the overall system, which is not just technologies, so that we may have inadequate detect, sense, and avoid technologies and algorithms which may impact the capacity of this to perform a mission without any danger to people and assets. Limited operator situational awareness is one of the issues. When you're flying these small vehicles, the persons that is flying them on the remote control will lose sight of them. Limited communications abilities. Again, this is very small. So the radio system in both ends are going to be quite simple, which means that you cannot communicate that much. And there's no bandwidth, almost no bandwidth. So you have to communicate, but a certain amount of data. Aircraft design quality is going to determine if this thing can fly anywhere, anytime, in any condition. Maybe not. With electrical motors, you can say we have a problem with aircraft construction quality. So if you have a good design to do the mission, that's one thing. If you have a construction quality, which means that, yeah, you could have a bit of humidity and this thing is rendered useless. So the challenges are the following. We have a small UAV. It may be unique. So we built a few and there's so much we can do with a small UAV. Because it's small and it's a small size, it's got low visibility by people, by others. And this includes other aircrafts. And this means this includes other drones. It's got limited payload capacity and it's got the primitive or limited manual control methods. Even with RC, there's so much you can do there, and there's so much capacity with the transmission and with the amount of systems that you have there. They're not expensive, and that's what you wish as well, not having them expensively. And this means they're primitive. Limited capacity for communication, and we'll try to put TCAS and DSB, and we'll see that later, but we'll see how hard it is. Limited capacity for sensor integration. Well, you've got limited payloads. You don't want to use all your payloads for 2 or 3 sensors. So this means you won't be able to do much. depending if you want to transport parcels between buildings in a city, for example. So problem statement, what are the risks involved with small UAV operations? That's the first question we should ask ourselves, and have been tried by my PhD students, and actually we answered to a certain satisfaction. So I will show you that now. What is the true assessment of these risks? So what can we use there to evaluate the level of risk that we're dealing with these venues? Can the small UAV ever possess an equivalent level of safety equivalent to manned aircraft? Big question, and that's what we should target. What safety DSA requirements would satisfy the ELOS requirement? Well, first we have to discriminate between the real risk and the perceived risks. So the real risk are what the people are going to suffer if this thing goes bad. This means that the risk to people and property on the ground impact. And there's a risk to other vehicles flying in the air. That's called mid-air collision. So we're the MAC, what we call MAC, mid-air collision. So this is another issue. We can crash on people on the ground, and we can crash on flying objects in the air. Perceived risks. Well, we talked about the reality. Now, the more problems we have is also with what the people consider is happening here. And sometimes this may be, we know with the medias and everything that we can have risks which are shown bigger than what they really are. So we have to understand and address the perceived risk to ground crew, high operational costs, so people perceive that highly, and financial risk due to attrition. So people don't want to spend that much money. So, and even if they want to be operating safely, they will cut corners. Okay, fear of crashing. Well, fear of crashing is when you are in an aircraft, but then if they start flying over your head, you fear that they may crash on you. And when you operate them, you may fear crashing on others. Public acceptance, fear of the drone. Okay. Oh, well, if you put a machine gun on it, will they start killing everybody around in the city? So privacy concerns are also very high, especially in the countries where your privacy is very highly considered, where your freedom is highly considered. Then the people will start to think about shooting down your drones. That's been seen. So what's the estimated ground impact risk? We call that ELS on the ground. So on what we're going to go with that. And then we're going to talk a bit about air-to-air collisions. So ELS ground, and generally speaking, is 1 over the mean time between failure multiplied by the ground area exposed to ground impact, the population density multiplied by the penetration factor, and the mitigation technologies. Mean time between failure is something we see a lot in mechanical engineering, because this is what we assume is going to the next time this thing will need to be repaired, and it's going to there's going to be a mechanical failure. This can be evaluated depending on the quality of the design. And of course, this means causing a crash if it fails. Exposure is a ground area exposure. If you're making a mission which is around an offshore platform, you can say the area you're going to be flying over is the area of exposure. Population density, well, if you're flying over a platform, this may mean that its population density is the amount of people you see over a surface space there, in cities, in the ground, on farmlands, over farmlands, or over open areas. It could include the Arctic, for example. Penetration factor, this means how hard this thing is, how strong this thing is, how much likely this thing is going to create damage if it hits anything. The mitigation technologies, do we have anything on the drone that may, if something goes wrong, this could help save the day, like, for example, parachutes, emergency landing units, or nets even. We're operating with nets, so we could just net it out. Here's the estimating ground impact risk according to our tests and evaluations using that function there. So depending where we are, here we have different places which are related to Canada and especially Newfoundland. So the lowest part is Labrador. So Labrador is like some islands or some parts of the Scandinavia which are extremely low densely populated. And this means that you have almost nobody per square kilometers. So these are the level of risks that you find there. And then there is Newfoundland and Labrador together. So the whole surface area, the populations divided by the space it covers. And when you know how sizable is Labrador and Newfoundland, then it makes a big space and it gives you an idea of the risks which exist. And then you have Newfoundland itself, the island of Newfoundland, which has a lot more people, and because there's about 5,000 people in Labrador and there's about 50,000, so 500,000 of people in the area of Newfoundland. So this is going to be, and then you go to the next step, which is here we have Newfoundland, and here we have Greater Toronto area, or you could say Greater Toronto or Greater Montreal or Greater Vancouver. These cities have something similar in terms of sizes and density of population, well, sizes, because depending on populations there, this is going to give you this curve. According, on one side, estimated level of safety, so the number of fatalities of accidents, likeliness per hour, and the mean time between failures of the machines we're operating from. We'll focus on the 1,000 here line and the red line, which is the target, the ideal target of 1 to the power of 10 multiplied by 10 to the power of -7. The actual fatalities per hour, according to Statistics Canada in 2012, is 2.3 multiplied by 10 to the power of -7, which is very safe, safer than going outside during a storm and being electrified. Okay, so here you have also, then after that, Toronto, you have the metro area of St. John's. So that's Toronto, that's metro area of St. John's, the city of St. John's, and then that's St. John's itself. So the area of the city, the municipality of St. John's, where there's a bit more density, and then there is Toronto. And Toronto is if you think about that, just the city of Toronto with everything, including the city center with the buildings, that's a surface with a certain amount of people, 2 million, and that gives you these values. Of course, you have more densely populated cities, like you could say, where do I put Manchester? Where do I put London? Where do I put Paris? Where do I put Lyon, New York, Berlin? Well, you can put them, Tokyo. You can put more and you can evaluate these things. You can imagine New York would be very high up here because of the extreme density of Singapore with a lot of high-rise, or Shanghai. So you could have that here higher. So this gives you, for 1,000 hours mean time between failure, which is reasonable for most of the small UAVs, then these are the values you will obtain there. So you would be only able to fly them over Labrador and Newfoundland and Labrador. But then Newfoundland itself, when you start considering Newfoundland, starts to be an issue. Definitely not over cities. Okay, so this gives you a good idea. So now we have an estimated mid-air collision probability, which is very essential. Okay, so we have the one for the ground and we have the ground for mid-air. And that's another one when we fly over. Well, we have P-enc, which is the probability that an aircraft will encounter another, okay, related to air traffic density, which is the result of, Pmac is the result of that multiple factor. That factor is air density. You can have data for that. It's all recorded according where you fly. If you are in a zone, and depending on the altitudes, if you're cruising at 12,000 meters and you're over Glasgow, well, you're going to have all the European aircrafts flying from Europe's capitals to North American ones, and even further. So you're going to have to be careful where you fly, because these values may change according to statistics. Probability that loss of separation occurs, okay? And then, of course, this also can increase the likeliness of an accident. If this thing is lower, depending on the equipment that you have there, okay? A probability that UAV fails to respond to the threat of collision, and probability that manned aircraft fails to respond. Here, we have one about manned aircrafts. That means that when we have a UAV versus another UAV, we can evaluate that very precisely. But then the probability of a flying Boeing being capable, or Airbus being capable of detecting my small UAV is going to be put there. It may not be able to respond to the likeliness of an occurrence of a small UAVs. So you put that in there. So there's different aspects to take into consideration. And the P-ENC here needs to be further examined according to airspace. I'm not going to review all airspaces because some of them are forbidden and are very difficult to approach. But the one of interest is the G airspace, which is general aviation airspace, or G class. And then we define an area, we define an altitude H, and we have a UAV path evolving on that path there at a certain altitude. They may have a certain thickness of altitudes, but normally when we operate at a constant altitude. So it's going to be N divided by V class multiplied by V trans. N is the number of aircraft present in the airspace. And again, this is data that can be obtained from statistics. V-trans is the selected value depending on if we choose Mach or Nmach. Nmax means a 10 meters diameter around the UAV, and Nmach is a 300 meter diameter defined around the UAV. So this P-ENC may define if we're concerned about Mach or Nmach swept through. Okay, V class is the diameters of G class airspace up to 2,200 feet or 670 meters. Okay, and that's the type of volume we evolve in. Okay, and now we can go near airports, and we have C and D class airspace. Some airports are the densely populated airports and the low density airports, which are still an issue because you are having small aircrafts, but you still need to worry about that. So the only difference is we are going to introduce a new term multiplied here, time spent in the zone in an area where we have the likeliness of encountering N aircrafts in that zone. Again, statistical data according to time of the day and everything. If you're passing over an airport at, let's say, 5,000 feet, well, you are 1,500 meters. What you happens to be is going to have, if it's 2 o'clock over Glasgow Airport, at this time of the day, N will be a certain value. That's recorded. And then the time it takes for your aircraft to go through the zone at the cruising speed, 150 kilometers an hour, over that space, that radius there, you can calculate very quickly all these values and then have an idea of the P-ENC. P-ENC are being recorded here, P-Mach, P-ENC Mach, P-ENC Mach, P-ENC and then Mach, and with the P-Mach and the P-N-Mach. So probability of near miss and Mach, worse than Canadian statistic and CNG airspace. Probability of collision, so this means you're in there and you're going to crash. 10 meters distance is so close. This means you're crashing, and that's what we do with the Mach. When we have reached the point of a Mach, we consider that a crash. Okay, because it's too close for comfort. It's too close for a reaction from the pilot. If it's an aircraft that sees something flying back, this is considered a crash. Okay, luckily the guy didn't hit him, but then depends the heading of the aircrafts most of the time. But we're not going into that. So better than Canadian statistics, but worse than the target level in CNG airspace. Conservative estimates of probabilities, assuming no safety equipment or DSA, but help from ATC and control zones. So you could have air traffic control, which may help unmanned aircraft in certain zones, especially the C and D zones. So if the air traffic is going to relay the information to the manned aircraft to say, you got the 3 drones in the area and they are here, okay, because he's aware of it, because there's maybe instruments in the drone to relay the information, and the guy in the control tower is going to make sure they relay the information. Okay, enhancing control and situation awareness. Well, we have that possible. We have ways to achieve that. So first of all, there's manual control, the classic stuff that we see in every club, aviation club or the RC clubs, and the way small operations of UAVs are done in, for example, in cinema, they will use manual radio control methods and with small UAVs. So you have a flight console similar to a dual pilot cockpit using a forward fixed camera view on the aircraft, on the UAVs, and it's what the military use, and they have big screens to relay that screen, that camera information. In our case, we have a small screen to relay the informations to. Virtual reality methods can be employed here for in various forms for like first person view. So you can have a camera, you can see the image from a camera in the front of the aircraft. So when you're flying, well, this is what you see. And it's increasingly popular with RC hobbyists, but it's more expensive. And you can have an ENS HUD type of things where you get information around it. You can even have simulations aspects. You can have things shown inside, which are known to be there anyway from the simulations information. Okay, it goes up to a certain degree of safety, but you know, as soon as you have a distance from the UAV, it becomes difficult. Then we have the UAV control modes, automatic control, where we can go in full control and we can have GPS-based autopilot. As we are in the outdoors, it doesn't go indoor. So we are going to use other ways indoor. So, but here we're talking outdoor. GPS-based autopilot control using waypoints to define a flight plan. So we have our points and we have a GPS relaying our information so we can have a feedback with the GPS information. Or we can have an inner loop inertial airframe control that's called odometry. So we update accelerations, we update from the change of positions from the original positions, we update the positions. And this is one way that usually as well. We can have automatic takeoff and we can have automatic landing offered by some autopilots. It's offered, automatic landing is offered in airliners. A lot of times takeoff is not offered, but landing is offered. So we can use that as well, but it's a bit more sophisticated. And takeoff and landings are a big issue and are the object of research, especially takeoff. It's one of the critical aspects, which is very difficult with automatic control. Autonomous control, complete autonomy, meaning that you program the robot, you send it on a mission, it comes back and it's ended and it took care of things, whatever happens. That's research. That's open to research, and we are not doing it yet. But the military does it. Military do these things, but in the civil operations, we're not. We're not allowed to do it anyway, not yet. So we have to improve everything we do. So remote control is you have a person with a remote control unit transmitting radio data to like here an aerosound, and you're getting information from its positions, well, its pose, so position and orientations there, your pitch and roll, and you're getting it back. And with you have an elevation at which you are going to see, so that's your line of sight. You have a range, which is the one on the ground, the distance on the ground, the altitude, which is the vertical distance. So line of sight is going to give you with the informations an idea where it's going. The pilot can only manage up to 8 variables at one time from a remote perspective. Otherwise, it's sensory overload from a human perspective. At extreme range, we have poor visibility and it's almost impossible. In other orientation, control becomes difficult. Imagine it's not facing in the same heading as yours, then it becomes very, very hard. What if the view is switched to a first view? Well, we could use a first view with a screen or a big screen or even an overhead display. Then we can measure that and see the different ways. So the ones in blue here is the result for remote control from the side with a distant view, the flight simulator type of thing. So with enhanced screen information that is coming from the aircraft with the camera in the aircraft giving you a vision, and then VR goggles. So you improve that by putting that right on your eyes so you're not having any impact from the surroundings. Okay, so we have two ways to measure that. So we had the landing strip. We got an expert and a rookie to land the aircraft, the Aerosound or the giant big stick, and we landed that on an airstrip, which was a former military airstrip. So it's a massive one. It's a huge one with quite a bit of width, 40 meters by a bunch of kilometers there. Here's the precision of the 3 types modes. Precision meaning in terms of landing distance. So are we having a short landing or a long landing? Are we having a deviation from the center line, which we try to target? In windy conditions on top, in calm day below. And this is data we've obtained through thousands of testing Well, there's only a few there, but we did many tests on those things. So landing, touchdown on a calm day, and there. So you see the spread of the different techniques there. For the RC mode, we can see the spread of the, it's not that bad, but it's that there's a tendency to undershoot, so to arrive too early. And on the flight sim, there's a tendency to overshoot slightly. And with VR goggles, we're not improving things, actually. We're actually undershooting quite a lot. And then, of course, there is the landing distance, the centerline deviation there, which is also shown by the green and the right and the blue. And well, the results are this. And we can see on the windy day, what does spread is actually under or overshooting according to technique there. On the windy day, deviations from the centerline Y is very good. Touchdown distance is not helped. RC mode is most accurate for the veteran pilot. On a calm day, it's worse than a windy day, actually. We're not doing better, especially the VR mode. And faces problems with the FC mode setup. So there's issues there that happen. Evidence of large blocking effect, depending on the 2 different days. So there are different things that could make you block access to information and have a good appreciation of things. And some other factors may be affecting, like the glare. Like you can see, a flashy sun can erase the features and the possibility to have information and actually identify objects and to be precise about things. VR, well, this is the stuff we use there. So this is the, when you are using a HUD display or when you're using the one on the screen on top, or if it's overhead display. And this is the giant big stick that we use there with the camera on top here. And this is the image. So if we use FPV methods, the accuracy has been improved. If the VR mode now is the best method on the proper runway. If you combine landing touchdowns positions in 2013 with better systems that we have here, is the VR mode is now the best. The FS mode method has improved the centerline deviation, but still long landing. So we're overshooting on the landings. The novice pilot had a lot of problems with the FPV's modes and especially the virtual reality ones. And the poor weather forced us to end the experiments a lot of times and that's one of the things we want to be able to operate UAVs in bad weather, but still, depending on the quality of the machine there, we may be in trouble. So, and then we have to be talking about enhancing visibility, and there is an issue of daytime, and there is an issue of nighttime. So the human eyesight is affected by the background luminosity. As you can see, if it's a sunny day, it's going to be glaring, and I'm not going to see the details in the background. I'm not seeing what is happening on the wall there. It's blurred. I've seen that with vehicles had cameras in the back or in the front. Depending what the sun is, well, you can have issues. So autonomy could be affected by this. So contrast during daytime is difficult to obtain. And depending on the weather conditions and overcast clouds allows you to have sometimes better, but don't be too close to the clouds and don't have them too gray. If it starts to rain, that starts to be a problem with luminosity. The detection limit is about 20 to 30 arc second. And if you want to distinguish shapes, you need to be having a 4 to 5 arc minute. So when you go further, it's going to be bigger. So otherwise, smaller objects, impossible. Normal humans' capacity for visuals is 200 degrees because you can turn your head, 135 degrees elevation. High-res vision is limited to only plus or minus 15 degrees. So for small UAVs, human unlikely to spot beyond 500 meters range, and only in the narrow FOV with maximum acuity. So without glasses, much worse. Good glasses, good conditions, good weather, good everything, 500 meters range to detect a small UAV. That's becoming difficult. Off-axis approaches are dangerous, even for full-size manned aircraft. So it is even more so with the small UAVs. And if you're flying it with a visual and if you're off axis, it's going to take you a while. It's like when you're using binoculars trying to watch for something, you may not see where you are at all. You may see something and may not be able to recognize it. So you may be lost. And you may have a hard time realizing, oh, I just lost my runway axis. Oh, good, I have to come back. Okay. And then you have nighttime. Nighttime, well, it's dark. So if your airplane is dark, you won't be able to see it. So impossible to detect. So you have to have navigation lights from 5 to 40 candelas intensity, and they are visible at 15 kilometers in the front and 10 kilometers maximum to the side. Anti-collision strobes improves things, so they have to be 400 candelas visible to 20 to 25 kilometers and in ideal visibility conditions at night. So this means no rain. Going to be difficult in places like Scotland. So anti-collision strobes, 400 candelas, visibility with atmospheric effects will attenuate and will reduce tremendously very quickly. So nighttime light detection is average naked eye acuity of 4 hours per minute, like in astronomy. We are all just confirming what the astronomy people live with. And for the aerosonde with a 3-meter wingspan, which is quite a long wingspan, with these flashing lights there's a limit of 2.6 kilometers to resolve the individual wingtip lights. Beyond, further than that, you see only one flashing light and you don't know what is happening with the light because it stays flashing even if it moves in the axis. For if it moves sideways, you may say, oh, something is flying there, but you don't know the details. So that's an issue. You can improve that by using detection enhancement, and most of the aircraft use transponders, and they can relay information about the cockpit to the other cockpits and to the control towers. And then simpler versions are called ADS-B, and we've tested them on the Raven project, and they allow your smaller UAVs to transmit informations to the others. But then if you have ADS-B, not everyone has ADS-B, and an airband radio which can send a signal, a message saying, I'm an aerosonde and I'm flying here. I'm flying close. I'm flying close. So an aircraft can listen and hear, I'm flying close. I'm flying close. So regularly you receive a message telling the towers, telling the airplanes, there is an aerosonde in the vicinity and it's not far because I'm hearing it. So that's what radios can do to enhance. And of course, there are 4D simulations environment for collision avoidance, which can be used. Where we can try aircrafts with sense and avoid systems, but most of the times we won't be able to test them all the time. We will have to do that in our labs or in our venues, in our company. And this means that you're going to have to simulate your systems and try to see if you can avoid collisions. But to be able to simulate with the proper AeroSim or GSB-SIM model, well, you have to check if your model is real and is working precisely. And then you're going to have to show that you can send two simulated aircrafts on a collision course, which is not that easy to obtain. So you have to prove that in your simulation model of the dynamics of the aircrafts. And then on top of that, you have to put your control strategy that is going to show that it can avoid the crash. Because more complex. These are interception and avoidance strategies which are used and which we examine in our PhD thesis, my students, and we have different types of maneuvers which are tried. And remember, the UAV is a small aircraft, is not seen by the bigger aircrafts, so the pressure is on the UAV. The UAV, by rule, should not crash into another aircraft. Period. It's its fault. If it crashes, that's its fault. Well, the pilot did this and that. That's your fault. You should avoid at all costs because you've got 300 people in that aircraft. So whatever the pilot did, it's your fault. It's the UAV's fault, and that should be remaining that way. So in conclusion, what we have here is the current estimated level of safety of small UAVs. Reliably, we will have to improve the small UAVs systems, designs, construction, because they are quite cheaply designed at the moment. And if you really want to have something, we may decide to have GA level quality of design. So it should be designed as good as a Beechcraft, or even we could try to go as good the qualities of the airliners like Bombardier, Embraer, or Airbus or Boeing. but this is another issue. So at least we should claim ELOS with a GA aircraft. We should be as good as them versus the risk to people, property on the ground. So that's the main thing. We want them to be comparable in terms of level of safety as the GA aircraft, period. The small UAV should be restricted to very sparsely populated area for the moment because they're not reliable and good enough to be flying over our cities, over the densely populated, or special assets like power lines or nuclear reactors, or even we have to be away, not too far close to stations there. Okay, the small UAV does represent a slightly higher near miss risk in C class, and the mid-air collision risk does not meet goal under the value that we wish to reach for the events in terms of hours of per accidents in C and G class airspace, and is 4 times the risk in G class airspace for near miss cases. Okay, so there is MAC and NMAC. Already NMAC, we could try to do that, but MAC, we have to meet it. So it's no point there. So thank you for listening to this presentation there. Hope you learned something. If you have questions, you can send emails to this one here. And I'll be more than happy to answer the questions and even collaborate to improve all that. Thank you very much. Have a nice day and see you